Okay, so welcome back, lads. You're on your Lecture 7 week 5. So far so good. Labs are going well at the minute, so let's keep that up. Again, as always, my email is on the front of the slides here, so if you have any questions, don't be afraid to send me an email. Get on to Edmund or Maria as well in your labs. We'll be able to work out whatever is wrong or sort out whatever we need to do. Okay, so here. First thing we're looking at here is a bit of a recap, same way we start all our lectures with a recap. What we've done so far and a bit of explanation as to where we're going with the lecture today. Okay, so we've looked at Ireland's history and wood, we've looked a little bit about silviculture, you've created your posters, that's your application principle 1. One of your posters is a little bit about silviculture, how you plant forest and what the forest is going to do for people. We've looked at growth of forestry, we've talked a little bit about the scientific method and why it's important to you. We're looking at the use of wood, so normal uses and innovative uses. We're starting to look at the growth of wood, and then we've looked a little bit into the cellular structure of the tree. That's something we're going to dive a little bit deeper into today, and hopefully trying to develop an understanding how that's actually going to affect us as teachers in the future, and how it affects how we actually design and manufacture different products out of wood. So this is your application principle 2. Okay, so right now your application principle 1 is going to be due for your next lab. This will be similar. Okay, so there is a timeline for this. It's going to be due for your lab that suits that. Okay, so in your first application principles submission, you detailed your approach to growing a forest close to a nearby town. There is a secondary school just down the road from the forest that you're actually talking about planting. You have been tasked with creating an A3 sized infographic which explains the mechanism by which a tree grows. This is to be displayed at the entrance of the forest and designed to educate students in secondary schools. Okay, so this is directly related to content covered in lectures on tree growth, and the infographic must be submitted as a PDF. So the infographic will be submitted as a PDF in your lab time. Again, you can sketch it, you can use PowerPoint, you can use slides, you can use digital graphic programs, whatever you want to use to present your information as best you can. Very similar concept to that with CBA. There's no exact method to present your information in. As long as we have an infographic that can be displayed outside the entrance to the forest that you're talking about planting. Pay attention to your target group. Pay attention to what we're asking you to talk about. So we're looking to talk about the mechanism by which a tree grows. Okay. So just from looking at this, I want you all to take a chance, take a bit of time. Pause the lecture now, scan that QR code or copy and paste the link. That QR code will bring you to a Mentimeter, and I just want you to fill out some of the words that come to your mind when you start talking about, or when you start thinking about the mechanism by which a tree grows. The kind of a mind map there on the side is something that was created last year by a couple of people. What do we see? What's important with it? How does a tree actually grow? Are you going to directly relate it to species you're planting within that forest? What else could you maybe include in your infographic? Completely up to you. All right. But I just want you to complete the Mentimeter so I can see where your thinking is at, and then I can add to my mind map here. All right. So this is something we're going to start looking at now, and it's something I want you to try and create a connection between the cellular structure of a tree, the mechanism by which a tree grows, and how that actually affects us when it comes to creating projects. Okay, so ultimately this is what we're working towards. We're looking to get a deeper understanding of the structure of timber, the cellular structure of timber, of wood, and how it actually affects how we design and manufacture things. So if we just flip back and we're looking at this image here on the right hand side, okay? So these are different, obviously, boards that have been converted from the tree. We've kind of true and true boards here. These are most definitely true and true. That's true and true for sure. And we're looking more here at a radial board, even though it's going through the pit, it's more kind of radial, or quarter sawn possibly. Similar here, we're looking at a quarter sawn board. We're looking at the same quarter sawn board laminated together the opposite way around. We're looking at two possibly radial boards there. We're looking at true and true here. True and true board that's been ripped and laminated together side by side with the sapwood. And then we're looking at two pieces of they could be they're probably sections of a true and true board that have been ripped out, but they're being laminated together into a beam with either the pits opposite each other or the pits facing each other. So all of these examples are clearly understood, and you can see the grain pattern. You can estimate yourself where that piece of timber has come from on the tree. But what you need to pay attention to is, yes, some of these are exaggerated. Some of them are not exaggerated. We've all seen boards cup this much. But why are these boards cupped in this direction? What is affecting it? You know, when we start thinking about how much heartwood is in each board, how much sapwood is in each board, when we talk about species that we see that are likely to warp and cup, are they fast-growing trees? Do they have large trachoids? Do they have large vessels? What can we see? You know, what do we see from these images, and what are we gathering from our deeper understanding? You know, when we look at this true and true board that's cupped away from the heart of the tree, what are we looking at? We know we've got a lot of sapwood here in the center, or heartwood in the center. We've got our sapwood to the outer edges. Why does that want to shrink and pull away from the pit of the tree? What do we understand about that? You know, when we look at our quarter sawn boards here that we would commonly say are used for flooring, why are they shrinking more towards the earlier growth, or towards the later growth, so the sapwood, than they are at the heartwood? Is there as much moisture within the heartwood when the tree has been chopped and felled and converted? Or is there more moisture in the sapwood? Does that leave more space for shrinking? What is causing this? And then how does that affect you when you start thinking about how you're going to make projects? Same here. So we're looking at a cross section at the end of a tree here, and we're showing the shrinkage and how that actually affects our pieces when we cut them. You know, we can see, we all understand that that's a radial board, or I believe that maybe they're trying to show us a tangent, or a true and true board. It should be the full width. They're trying to show us a full true and true. But I think they're trying to show us a true and true here, and the fact that it's cupping away from the center of the tree. We're looking at a true and true board going right through the pit here, showing us that the pit has less shrinkage than the more outer parts of the sapwood. We've got a radial board here that has very even shrinkage. We can look at that later on, and it's to do with the orientation of the piece of wood within the tree itself. Here we're looking at more true and true boards. There's in a different orientation. We're looking at a quarter sawn board here with a larger radial section. We're looking here again at a quarter sawn board, or maybe a tangential sawn board here. What are we looking at about the shrinkage? What do we notice? Is there deformation? There is, but we need to figure out why that's happening. So you can say, oh, it's shrinking, but why is this not shrank in the opposite diagonal? Why is it shrank in this diagonal here? You know, what kind of amalgamation of grain or amalgamation of cell structures are you getting within that certain area, or within that arc of the grain pattern? Why is that collaboration of cells, you know, allowing for this shrinkage to occur? And then one of the last questions we want to look at here, or get you thinking about, is this is something that's become really popular now, you know, TikTok and Instagram and all that crack. End grain chopping boards. Why are end grain chopping boards not, you know, the most sturdy or most reliable design or structure of a piece of kitchen utility? Like, why is it not that strong? Yeah, like end grain chopping boards have to be maybe 2 or 3 times thicker than a standard chopping board. But why is that? It's not just for design. It's not for features. It's not. It's obviously counteracting something. But what is it? What is it, you know, allowing for? I'm sure we've all heard the term short grain, and short grain being a point where things can break and crack. But usually we talk about that when it talks to joining materials. We're joining materials here. But what else do we understand about this? You know, what about the structure of the tree now? The xylem cells and the phloem cells. You know, what about the trachoids and the vessels? Are they linear? Are they horizontal patterns? Why are they able to separate in certain ways? What actually helps to bind these together? Where is our structure? Okay. So they're just prompting questions just to get you thinking. There will be questions about them in later on, and you will be asked to basically express your understanding. So just make sure you're thinking about that. It's just a bit of food for thought for a minute. Okay, so this is where we're going to start getting into the more heavy parts of tree growth and cell structures. Okay, so basically this infograph here, or this graphic here, represents all areas of tree growth, and regular and irregular parts of the tree, as well as standard parts of the tree. Alright, so we're focusing in kind of on the diversity of hardwoods and trachoids at the minute. So we're going to be looking at fiber cells and vessels for this lecture, more or less. Okay, but you will at some point be coming down towards this area here where we start talking about non-standard wood, so mature wood, juvenile wood, reaction wood, and other. So we'll be looking a little bit about stresses within the timber, how that affects the grain pattern, and how it affects the material and the cell structure. We'll be looking at tensions and compressions, and then we'll be looking at, well, we won't be spending a lot of time looking at a burr. I'm sure you'll understand what that is. You know what it is in your own mind anyway, from imagining it or seeing them in the past. But we will be spending a bit of time when we talk about tension and compression woods and reaction wood. Okay, so keep going with this now. This image here is showing us a sample of some reaction wood. I'm not going to tell you compression or tension, but I'm talking about reaction wood. This is a coniferous tree. This is a cross section of a sample of a piece of yew. And the reason I've shown you this image now is I want to know, would anybody make an estimation as to why the pith of the tree is not in the center? Obviously, it is reacted to something. If this tree was to grow on a perfectly level bank, on a perfectly level piece of ground, the pith would be in the center of the tree, and the tree would be of a regular dimension all around it. You know, we'd be getting concentric annual rings basically. Whereas we're not getting that, you know, structured design or structured layout within the end grain section here. So what has caused that? You know, and this does differ between coniferous and deciduous species. Okay. Now, so we're looking a little bit more at the fine features here. So common features between angiosperms and gymnosperms would be the vertical features and horizontal features within them. So what common features have we got? We've got trachoids, we get them in both angiosperms and we get them in gymnosperms. We get diurnal rays in both angiosperms and gymnosperms, although they're more prominent within angiosperms. We also get our vessels, we also get our fibers. So there's a lot of common features within them. Alright, but looking at these 4 images here, we've got 3 cross-section images of angiosperms and gymnosperms, and then we've got a longitudinal section. Okay, so cross-section is looking across the top, same as cross-cutting a piece of timber, and then longitudinal would be our understanding of, say, a rip cut with the grain. Yeah, so this would be our longitudinal section view here that we can see. This is a close-up of longitudinal, and we've got a cross-section here, and then longitudinal. Right. So looking at these different samples, what can we see within the images? Okay, so we dove into this a little bit in the last lecture. We had a look. We could see trachoids and their kind of baffled wall structures within here. We could see large vessel areas in this cross section here. We could see some large vessels. These gathering of large vessels would lead us to maybe believe that this could be an angiosperm, something similar to oak or ash, where at certain periods of its growth cycle, it needs to transport a lot of water very quickly up through the xylem, and it will do this using vessels. Okay, vessels are a one-way system. Trachoids can be 2 ways. All right. What we do want to talk a little bit more about within the trachoids is why are they so, or what kind of structures do we see within them? Okay. So within the trachoids, we have kind of a very thin wall. Okay. we have a thin wall that can actually go and what's the best way for me to explain this to you? So trachoids have very thin cell walls. Okay, and they can change structure, and they actually do repurpose within the growth cycle of the tree. Okay. For the minute, the main thing to realize is that they produce structure, and the actual cell of the trachoid is more than just for transport materials. It provides structure within the tree, and it has a very fibrous build-up within the structure of itself. We'll be flicking on and having a look at that in a second. The other thing we're looking at here is diurnal rays. So if we can get a look at here in the top right image here, there's a horizontal line coming through the longitudinal section. So that's a medullary ray, okay, or a ray cell that you might have heard of. All right. The purpose of a ray cell, the main purpose of a ray cell, is the storage of starch or food for the tree. Okay. So we're focusing on the storage of starch within the diurnal ray cells. Okay, or medullary rays. So the trachoids. So In gymnosperms, they're very simple, primitive forms. Angiosperms, we rarely see trachoids, but they do exist within the tree. They're a more complex kind of structure, and then vessels and fibers evolve from the trachoids within the tree. Okay, so you would very rarely see the trachoids because they're constantly being developed and they're getting turned and used again for vessels and to be used for fibers to kind of give the strength in the tree and give the structure of the tree or transport the materials within the angiosperms itself. Okay, so this is our kind of basic structure of the trachoids. All right, this is within the angiosperms, so it's the most basic trachoid, and it does diversify. It has fibers, so there's a thick cell wall that has a lot of fibers within it, giving the tree its support and its strength and its structure of the kind of woody flesh of the tree itself. If we look at our cross section here and our cross section including the longitudinal, we can see we've got our trachoids as these smaller circles here, and when we look at the longitudinal section of the trachoid, we can see the interwoven kind of baffle walls that we talked about before, and we can see how much structure and how much strength could actually be developed within this dense structure of the trachoids in comparison to a vessel here where there's a lot less structure. It's a much wider, much broader cell. It's given less support to the tree, less ability to actually maintain a shape and a structure. So certain species like eucalyptus or oak can have weak points where there's a large clump or large gathering of vessels, but the inclusion of trachoids will help to give structure and help strengthen the tree. Okay, so starting off with trachoids. Trachoids then can diversify either towards fibers or they can diversify towards vessel membranes. Okay, so starting off as a trachoid, the tree will have started its growth cycle. Trachoids are there. They're allowing for transportation of water, minerals, and food within the tree. As that tree hits a growth cycle, it will need to produce, say, a vessel. When it transforms or diversifies into the structure of a vessel, it broadens and allows for larger amounts of water to be transported through the xylem tissue. As these cells are being turned into vessels, we're creating weak points. The trachoids will also need to diversify and become more fibrous to support more structure. When they start to become a fibrous material, they almost become a dormant structure. Yes, they are still transporting food and material, giving strength and structure to the tree and keeping up healthy natural growth. However, the fibers are more so serving the purpose of structure for the tree and strength in the tree itself. So, storage cells now is what we're kind of having a look at. Horizontal elements that we can see within the tree. So the medullary rays or the parenchyma rays, they're the same thing. All right. So ray parenchyma, the storage cells, they store starch. That is their main purpose, is to store starch. So they remain alive for a very long time. They're one of the reasons that certain species of trees can endure very harsh conditions or long periods without any additional help regards growth. So within angiosperms, angiosperms need very large stores of energy in the spring. Okay, we're going to talk a little bit about that now in a second. Why? That sentence there. So angiosperms need large storages of energy in the spring. So the spring, when we think about what is happening within an angiosperm in the spring. So in the angiosperms, we're talking about a deciduous tree. So for example, if we're talking about an oak tree or an ash tree, and we come to the spring. In spring, there's nothing on the tree. All we have is a few buds. And as the buds are starting to grow, the tree's obviously having to use energy to create these buds. And while that energy is being used, there's no more energy being created because we have no leaves to allow for photosynthesis to take place. Okay, so once the leaves are generated and have been created, photosynthesis can start to take place, and more starch or glucose, or basically food and energy for the tree, can be produced, and the tree can grow at a more general, more controlled rate. How do then buds start in the beginning? Where does the storage or where does the energy come from for the buds to begin their growth cycle? That energy is stored within the parenchyma rays or the medullary rays. All right, they basically act like a battery for the tree. If you wanted to break it into your own simple terms, they would act like a battery, a storage location for food. So the medullary rays or the parenchyma ray cells will store large amounts of starch, which will be then used as energy. So come to spring, as the tree needs to start its growth cycle and the weather starts to warm up, the medullary rays will release the starch, and the tree will use that energy then to start growing again. And it's like a kickstart or a jump start off the battery. It starts growing the buds. Once the buds then develop into foliage, the foliage can produce normal healthy food again, and the tree can continue its growth cycle. As that tree is growing, it is important that them starch reserves are replenished so that the same cycle can take place again. It is very rare to see a medullary ray in a gymnosperm. Why is that? If we think about gymnosperms, we're talking about coniferous trees here. If we start talking about a Sitka spruce, which is an evergreen tree, it has its foliage all year round. There is a continual level of growth, even in the winter. Yes, it's a reduced pattern of growth, but there is a continuous pattern throughout the life cycle of the tree, where the tree has the ability to produce glucose through photosynthesis. Not with angiosperms. With angiosperms, we don't have that ability because we have no foliage during the winter months. So that means we need to have some sort of a reserve or a backup in our medullary rays, aka our starch storage, to start back up the tree now again in spring. Okay, so that is the easiest way to break that down. It's the most understandable way to break it down, and it makes kind of the most practical sense, which I feel will suit a lot of people within our subjects ourselves. Okay, so we're talking a little bit about a thing called diffuse porous, right? So diffuse porous is something that you'll see within angiosperms, and it's when we start talking about vessels and trachoids, and when we look at them at the end grain. So when we're looking at diffuse porous, we can see large vessels and small vessels all within the end grain. Diffuse porous is where vessels form of similar diameter and radius during growing periods. Okay, so if we're looking at this cross section here, this is obviously going to be our summer growth. We've got large vessels, all of similar size, similar radius. This will be a diffuse porous, and we will only see that in angiosperms. Okay, this cross section here will be a gymnosperm. Yes, there is vessels and yet, well, large trachoids transporting water up through the tree. However, it's a very continuous growth pattern, giving us the understanding that this could be a coniferous tree or a tree that has foliage all year round. Whereas we're looking at our diffuse porous, where we have clear growth periods of kind of extended growth or rapid growth, which would indicate that this would be an angiosperm or a deciduous tree. Ring porous, gymnosperms. Okay, oh, sorry. Okay. So we're looking at growth features here. So features that we'll see within every part of a tree. All right. So we've got our rings. Rings will feature within any temperate climate. If we could get a climate that was consistent all year round, you technically might not be able to see the annual rings. They would be quite hard to see. Although there would be a reduced growth rate, it would be quite hard to see something that is, very consistent. So for example, if we were looking at a tropical rainforest or a tropical tree, sometimes the weather might continue on for a very long period of being a good growth cycle or a good growth environment for trees, and our actual annual rings could be kind of more kind of invisible to the naked eye. So if we think about materials like mahogany, if we compare mahogany to that of oak, we look at the annual rings in that, we think about the area in which them two species of trees grow natively. The annual rings are a lot more vague in mahogany. They wouldn't be as stand out because we have a very consistent level of growth within that area. Whereas if we look at that of an oak tree and we think about the growth pattern that we'd have here in Ireland and in a more temperate climate, we have kind of more set out seasons, growth seasons, and that's how we can get a clear understanding of summer growth and winter growth lines, or annual rings. Okay, so within our early wood, when we talk about early wood, we're talking about sapwood really. We're talking about it's growing within the spring. It has thick cell walls. It has large vessels. It's transporting a lot of material up through the tree. The late wood is a little bit more kind of towards the dormant side of things. It has a thicker cell wall and it has less radial growth, so it's not expanding. It's not creating more structure for the tree. It is the kind of center column or the structure of the tree itself. We're also going to be looking at things that are called abnormal features of trees. We're looking at discontinuous areas like local inactivity of the cambium layer. So that's talking about maybe a damaged branch which has created a dead knot within the tree, so it's not working. And then we're going to be looking at talking a little bit about an event that could affect the tree's growth. Okay, so things that might actually affect the growth of a tree. So a late frost, attack and recovery, drought, rain, warm autumns. So how do these different things affect how a tree is going to grow for us, and how it affects the cell structure as well? Okay. So, Heartwood and sapwood. So sapwood has live parenchyma cells and has a high moisture content. The heartwood will have dead parenchyma cells and anoxic conditions. So that means no oxygen will basically be live within the heartwood. Okay, so if we think about sapwood and heartwood, sapwood is where all the growth is taking place. You know, all the xylem cells are being expanded out upon within the cambium layer. Okay, so it's all being expanded out. Within our sapwood, it's kind of the more wet area of the tree because it's transporting all the materials up and down the tree, giving it a chance. We will have more parenchyma cells, which we know are also called medullary ray cells, transporting the materials across the cross section of the tree towards the heartwood, allowing for healthy growth and healthy structure within the tree itself. And then we start to look a little bit about the bark. So bark, we've got dehydration, abrasion, attack. So we're defending from animal attack when we talk about that, animals, insects, and fungi. We've got cork, and then we've got a kind of a crusted phloem. So the outer layer is like, if you were to describe bark, the outer layer is is technically a crusted phloem. So it's dead phloem cells that have been pushed to the outer of the tree and has become hard and crusted, and it allows for this protection. The cork will eventually become the crusted layers. This bark is giving us protection from the animals, is giving us protection from abrasion. So if we were living somewhere where there could be a lot of sand maybe in the air, it would stop the abrasion coming in from that area. And then dehydration, it's actually helping to seal in the moisture content of the tree, helping to keep that moisture content up, allowing for healthy growth, especially in areas of drought. Okay, so if we're talking about converting timber and what we see when we convert timber, okay, one of the easiest ways to kind of get under a grasp of this, yes, if you were to look at a tree, you might consider it maybe as a cylinder, and we're looking at concentric circles within the cylinder and what happens when we cut that. But something that we have all seen and would be very clear in your mind at the minute would be conic sections. Okay, so conic sections, if we cut a cone in certain directions, we get different shapes. We'll get different developments here. So we get a circle with a horizontal plane, an ellipse. We can get parabola, we can get hyperbola. There's all different options. This same kind of concept applies when we start talking about conversion of timber and the orientation of timber when we cut it. Okay, so if we just take a look at these 5 samples that we have here. A cross section, we're obviously going to get an end grain pattern here. It's like an end grain chopping board that we see. This pattern here is a very prominent pattern that I'm sure you've all heard of. It's called a flame pattern. The flame pattern is known to occur when we have tangentially sawn timber. Okay. If we're looking at these 3 different knot examples, we've got a spike knot, an encased grown knot, and an encased knot. So an intergrown knot, and then an encased knot. So what are these different examples? We've cut basically a cross section across the longitudinal of a knot here. We've come across this knot at a diagonal. We haven't come through it completely perpendicular to the end grain of it. And here in an encased knot, we've come perpendicular to the end grain of the knot. These different knots will show us basically how the branch had been grown out of the tree and how we've actually converted our timber. Similar here. So if we're looking at our very first sample here, this is a piece maybe of red deal. We can see that the grain is very irregular around the structure of a knot. We'll be able to look at that knot and see it's very much a circle, letting me to come to the conclusion that we've actually created an encased knot here. So we've cut perpendicular to that branch, meaning that we may have actually come across here and done maybe a true and true board or a tangential board, but we're perpendicular to the end grain of that knot, okay, giving us that, and we can get a clear understanding of the disruption that the knot can cause within the grain pattern itself. Okay, something that's interesting as well is the annual kind of ring shape that forms, or the grain pattern that forms underneath the branch itself. Why is one side almost tighter or more compact and the opposite side looser or more available, or more space within that area? Would you be able to make an assumption as to which end of that tree was facing up, which end of it was the roots, which one was the crown, just based on the information around that knot? If we're looking at the macrostructure of a tree, so we're talking a little bit here about juvenile wood. So juvenile wood is very soft, very malleable, and it allows you for flexing and moving of timber. So that's something that's important. You know, as a species is young, if something happens within that forestry stand, that tree can be affected a lot, okay, and it can cause problems within the grain itself. So the early life of a tree is very important, that the actual forestry is maintained and taken care of, because if we go past a certain point where we've lost that ability to maintain the forest, and the forest has been affected by something like a landslide, or it's been affected by a large wind impact, or animals, or anything, it could be anything, that will in the end it'll affect the quality of material that we can actually harvest from that forestry stand in or utilize. You know, so if we protect it at its early stage, when it gets to a more mature stage, it'll protect itself. Okay, so prior to canopy formation, it's important. Okay, so it's basically the early or juvenile wood is before we get a canopy developed within the forestry itself. Okay, importance of height and growth at speed. Okay, so spiral grain, low density, and then high permeability. All right, so what I've done here is I've shown you 6 examples of different grain patterns that you can see within a tree when they've been harvested, when they haven't been maintained or haven't been taken care of, as well as a clear example of a good piece of timber. So number 1 is just a standard tree that has been taken care of well. It's grown on a perfect site and it's been quite healthy during its growth pattern. Number 2 then, we're looking at kind of an irregular grain pattern. So what has caused this? Could be vary in the soil type within its growth. It could be a vary in the environment that was around it. Did things change a lot during the environment? Was there light sources that were available at early growth that were then removed in later growth? Did that area all of a sudden become a floodplain due to large developments within a certain range? When we start looking at them, we can see a diagonal grain pattern. This diagonal grain pattern can occur because of wind. If the wind has kind of bent the tree and started to move it, the grain can actually flex in one direction. This can become very dangerous even when in the harvesting process. You can't tell this from the outside. From the outside of the tree, the bark all looks very similar. But once you start to harvest the tree, if there's any of these internal grain structures or internal grain patterns that are within the tree, they can actually break irregularly, or how you wouldn't predict it to break during harvesting, and has caused and can cause a lot of death or injury to people, or fatalities. Okay, so for a tree that somehow grew twisted, produces a log with subsequent boards or spiral grain pattern. So again, we get a spiral grain. Somehow it's twisted. Maybe the wind has hit it, or animals have rubbed off it at a very young stage and started to rotate it over and over again, or like that, it's chased the sun, or it's chased the sun or the light around another tree to try and get that light to allow for itself to grow as best as it can. But in subconsciously, it's actually affected its structure and reduced its likelihood to succeed in the future. Same with our last 2 methods here. So we've got our interlocked grain pattern, which is often seen in a roco, and anybody that works in a joinery has described this kind of interlocked grain pattern as being basically just a mean piece of timber where the grain is in different directions. If you took a plane to this and tried to plane it, it would be very much a curly kind of swarf. It would be very hard to get a clean cut with a plane across this material, because the grain is actually changing its direction over and over again. It's almost impossible to get a good finish off a blade, and potentially sanding is your only option if you want to try and get a good finish on this surface. Even at that, because the grain pattern is changing so often, it's quite likely you're going to see scratches within the surface, and you're going to have to work up to a grit within your sandpaper that's almost considered a polishing of the material itself. And then we're just looking at a wobbled grain there, or when the direction of the wood fibers consistently changes, the board has a wavy grain. Okay, so a wavy grain can be perfectly fine unless you're looking to do something like maybe build a hurl or manufacture a hurley. The grain pattern is more important for something like that. Okay, so what can affect these? The wind, the slenderness of the tree when it's small, any animals that can get in and rub off it, so that's just do a grading, and weeds. So weeds can even cause these problems, especially when they're saplings. Okay. Reaction wood is the next concept that we're having a look at here. So reaction wood is very much based around that first image that I showed you at the start, the piece of yew where the pit wasn't in the center, and we had large growth rings to one side, and we had more kind of tight areas to the other side. We've got coniferous and angiosperms. These are different, so the reaction is different based on both. So these 2 trees here are leaning to the left. Okay, the pit with the coniferous tree is going to be to the right hand side, and we've got compression wood on the left side of the stump here. All right, and then with the angiosperm, our pit is going to be staying to the right hand side, exactly the same as it is in the coniferous, but the longer grain, or the wider annual rings, is going to actually be tension wood now. So the way it works with the coniferous tree it's under compression. It's pulling the it's getting forced down by the tree, and it's getting pushed up by the sapwood on the right hand side, trying to straighten the tree. And then with the angiosperm, it's actually becoming tension wood, so the tension is actually occurring in these cells, and it's actually trying to hold the tree and stop it from going any further, but it isn't being pushed up from the other side. So it's not becoming compression wood, it's working as tension. It's basically working as a band to hold back the tree as best it can. Okay, and this affects the actual structure of the tree. So wet and dry structure of a normal cell. All right, and then if we look at we can look at reaction wood. So we're looking at compression wood, and we're looking at tension wood here. So we've got different amounts of fibers that we built up within the areas. You know, we get a very heavy cell wall when we start talking about compression wood, and then we get kind of a more fibrous structure within the trachoids or within the straw walls when we start talking about tension wood. So we can see that they vary. So we've got compression woods up here, we've got late wood and then early wood. Compression wood and tension wood will look very similar when we put them underneath the microscopes. Okay, late growth and early growth here, I just put them in. They're not directly related to these slides, but the understanding here is coniferous and angiosperms react differently to their environment. That will affect the location of the pit within the tree and can affect the grain pattern that you'll be able to harvest from that piece of material there. Okay. The last thing I want you to do before your labs in week 6 is I want you to read up to and including section 1.6 in the Brian Porter book. Okay, so Brian Porter is in your additional materials, it's all available on Solus. Brian Porter book, I want you to read up to and including section 1.6, and then I want you to complete the attached Google Forms there. Okay, so that Google Forms is very simple. There's only 3 little questions on it, and it's based about what's taking part in this lecture, and it's going to set you up really well for the labs in week 6. Okay, it's important that you get a bit of external reading here. So up to section 1.6 in the Brian Porter book will be very beneficial to you, and it's what I'm asking you to do. Okay, so thank you very much, lads. It's a short lecture today online, and Friday will be very similar. During Friday's lecture, you have your MCQ to complete. So the first half an hour of the lecture will be lecturing, and we'll be taking notes, and then the second half an hour you will be let off to complete your time, or to complete your MCQs. They will be open for the half an hour. You're all allocated within this time slot, so there should be no problem getting it completed. Okay, thank you very much, and I will see you all tomorrow.